Thanks a lot, Giuseppe. I wish to say that Giuseppe and I know each other ever since a few years, when we both started to participate in competitions to be graduate students together across Italy. So thanks a lot to the organization of the IGF, to Luca and to Professor Iacoviello. I would like to be a little bit away from the mainstream of the conference to present effects which are string gradients in a membranal regime that you can observe at the scale of cell aggregates. So the analysis is done together with a group of biologists from the University of Ferrara in Italy, and it goes, well, the outline is a little bit pretentious for only 15 minutes. In fact, the setup is for an hour talk. But basically, I would like to introduce you to the structure of the cells and cell membranes to describe what happens to cell aggregates when it comes to having external stimuli such as chemical ligands. So the whole story boils down to having predictive models to understand the nature of a cell. For example, whether or not the cell aggregate is healthy or affected by diseases. In particular, the experimental analysis is done together with the hospital of Ferrara, in particular the gynecology clinic of Ferrara, in which they go there and they extract immediately pieces of placenta right after the delivery. And on those pieces, they actually investigate whether or not there is the state of the placenta is fine. Of course, this is done a posteriori, but the whole idea is to have predictive techniques for early diagnosis, for the delivery. Why do we care about this as mechanicians? Luckily enough, 10 years ago, people from the United States discovered that when it comes to having the response of a cell aggregate to ligands, actually there are mechanical effects coming up. Well, the structure of a cell is basically this. You see that this is actually a schematic in which inside there is the cytoplasm of a cell. This is the outside of the cell, and so the interface between the outside and the inside is the membrane. You see, the membrane is like a large population of items, and the items are actually lipids, in which the head is hydrophilic, so it likes to be in contact with water, and the tails are actually hydrophobic. If you have enough concentrations of lipids in a watery solution, they decide to spontaneously self-assemble in a bilayer. And the bilayer actually does behave like a membrane, like a structural membrane. What happens in the actual real cell membrane? You have a crowd of different fellows, such as, for instance, proteins and receptors. The receptors, as it says the name, they do receive ligands from the outside, and they do allow the ligands to transmit information, which starts a chain of chemical reactions, and it originates the response. So, what happens actually when a chemical ligand hits the surface of an aggregate? Well, in this schematic you see the surrounding lipids of one receptor. The receptor is formed, this is called the beta-adrenergic receptor, but you have several kinds of receptors of the same nature. So you see those cylinders are schematic for helical domains, and in this case you have 7 domains. The external ligand hits the surface of the aggregate. A reaction starts, eventually producing the cyclic adenosine monophosphate, and actually in a regular, just in one individual cell, you have something like 200,000 receptors on average. And of course, the whole idea is that the given ligand is capable to react only with one population of receptors. You can have several population of receptors, but one ligand actually enhances the action of only one receptor. And the whole idea is that if you have the right receptors behaving in a certain way, you can judge the health, the health state of the cell aggregate. What about mechanics here? Well, when the chemical ligand hits the surface of the cell aggregate, among those 7 transmembrane domains, 3 of them do respond, if the ligand is the right one. The first movement that you can observe at that scale is actually a rotation, roughly speaking, about the axis of the 6th domain, together with a shear of the 6th domain towards the 5th. And of course here you have the mechanics, the mechanical fields are actually omega, the rotation, mu is actually the shear, h is the height in the current configuration of the membrane itself. So this is the complete picture of what's happening, and if we single out a situation of a single, the action happening at the level of the ligand, you see that the ligand hits the surface. This is, say, the reference configuration, roughly speaking flat. The volume interested by the action is basically the one surrounding the 3 active domains, potentially active domains. Then you can see that what happens can be viewed as a composition of deformation, basically. You have, first of all, a classical deformation coming up. So, for instance, you can have membranal and locally deformation and even local bending, very, very slight though. In fact, it turns out that there will be a strain gradient of the membranal deformation. Eventually having an identity mapping, so macroscopically the situation stays the same, but then here you have a rearrangement. So conformational changes at the level of the domains. So deformation and conformational changes altogether. You may say that, roughly speaking, you might have seen a similar situation in pneumatic elastomers, for instance, in which the bones of the elastomers do decide to rearrange according to the applied stress field, for instance. So, what's the final and complete plot? Actually, when the reaction of the ligand starts, so if there is chemical affinity between the ligand and the receptor, the whole chain of reaction starts, and the cyclic adenosine monophosphate, which is immediately produced by the conformational changes of those domains, does actually spontaneously divide itself in 2 parts. One of it remains inside the cell, and that's the intracellular CAMP. But part of it is transported away from the cell by transporters. Of course, what is important in terms of measuring the response of the aggregate are 2 items. The density of the population of the active ligands, actually the receptors, sorry, and the density of the population of the transporters. Both of them are important for the response. Of course, what happens here is that those guys also, they don't stay just there at rest. They move inside the membrane, so they diffuse throughout the membrane while responding. So the experiment to detect the cell response was basically at the macroscopic level in some sense, because you have a macroscopic well, and so actually there is a plate formed by several wells. Inside each of the wells at the bottom of it, there is an aggregate of cells which are basically flat because they adhere to the bottom of each individual well. And of course there is a medium. Here you see a bright blue color in which this medium has a given concentration of ligands. When it comes to considering the response of the aggregate, you can have 2 choices. Either fix the time and measure how much of the CAMP is produced, or let the time to be going and change the concentration of the ligand. In both situations, actually, what happens is that you hit the surfaces of the cell and the movements of the receptors start. How can you predict the strain gradient effects here? Well, actually, the surrounding membrane to the given domain, just by pure chance, could stay neutral when it comes to having shearing through thickness. So this is a very not probable situation. What happens most likely is that in zones in which you have just a given domain, at the level of the lipids, you see thinning of the membrane or thickening. So basically the lipid ordering or disordering around the movements, around the domains which are moving, may in fact cause gradient effects. Now, the quasi-incompressibility of the environment surrounding the lipids imposes that thinning and thickening correspond to actually having in-plane membrane deformation. To make a very long story very short, you may have basically that equilibria of your membrane actually is coupled with diffusion and conformational changes. So as Gao and Freund, who are people in our community, did for endocytosis of viruses, saw you have an entropic term in the free energy that here involves both the density of active receptors and the density of transporters, but also you have a membranal energy which is actually non-local. So if you do a dimension reduction of the energy of the lipid membranes, we did produce this result 4 years ago already, you spontaneously see that you have a non-local effect, and actually the non-locality is governed by the local part of the energy. So if via statistical mechanics you are able to evaluate the short-range interactions, the changes of those short-range interactions actually do influence the non-local part of the energy. Then you can just turn the crank of stationarity of the Helmholtz free energy. So for people who are in pure classical mechanics, this is the analog of the elastic energy. But here you have a chemomechanical energy in which even the elastic part has a non-local term. So that's why you are able to penalize strain gradients to predict what happens at the level of the aggregates. Of course, you give up to describe the situation at the level of the single domain. You actually operate with densities of both receptors and transporters. Thanks a lot.